All right, hi everybody. Welcome again to Math for Machine Learning. So last time around we talked about univariate regression, and this time we're going to talk about multivariate regression. So let's get started. So let's see. So there are a couple of different ways to include multiple variables in a linear regression. The first one is to have multiple inputs, call them x1 through xp. And the second one is to have more than one output, call them y1 through yd. And so here we are learning a linear function between a vector x in rp and a vector y in rd. And so that's represented by a matrix, which is d by p, right? So y is approximately equal to w times x. And just like we did for univariate regression, we're going to assume that all of our variables, our inputs and our outputs, are standardized, meaning that we've centered by subtracting their means, and we've scaled by dividing by the standard deviations. And that's why there's no separate intercept term in this equation here. If everything's zero mean, we don't need the intercept term. And so we'll just omit it because it makes the math easier. And of course, when we actually have to do predictions, we put the intercept term back by reversing the centering and scaling transformations. All right, so regression with multiple variables is just like regression with single variables, only more complicated. In particular, we would like to still minimize the value of, find the value of w that minimizes our average loss. So here, the average loss is the difference between the actual value of yt and the predicted value, y hat t. And that predicted value is w times xt. Right? And we're going to sum over all training examples t and divide by the number of training examples n. So to make life easier later on, to make the notation shorter, what we're going to do is make a matrix by stacking together all of our training data. So in particular, here's a matrix X, and that's going to have x1 as its first column, x2 as its second column, and so forth up to xn as its last column. And then similarly, y will be maybe a different height, but it'll still be stacked y1, y2, and so forth up to yn. Right? So same number of columns in x and y, but different number of rows, potentially. And so what we would like now, given this representation, is y is approximately equal to w times x. Right? And so what that's doing, matrix multiplication on the left just takes w and multiplies it separately by each one of the columns of x and makes that the corresponding column of the output. All right, so then our loss is going to be this thing here, right? The difference between y and wx. Frobenius norm squared divided by n. The Frobenius norm, if you remember, is the sum of squared elements of a matrix. So the Frobenius norm squared of z is equal to the sum over ij of zij squared. All right, and that's distinct from the ordinary matrix operator norm, sometimes called the 2 norm. But you know, it's a norm, or rather it's a squared norm, and it happens to be a convenient way to write the sum of the squares of the elements of that matrix. Now, another way to write the same thing, is that this is equal to the trace of z transpose z. Again, this is not, it's not hard to verify that these two expressions are the same. In particular, you can just write this out. So Z transpose Z is just, the sum over, it's a sum over the second dimension of Z and then of Z transpose in the first dimension of Z. And then you sum along the diagonal elements. That's another sum, right? So let's actually write that out. This is equal to the sum over diagonal elements I of Z transpose Z II squared. Sorry, no squared, just Z transpose Z II. And then Z transpose Z II is itself the sum over J of, so we're taking the dot product of a column of Z with itself, right? So that will be ZJI squared, right? Which is the same as this expression here. All right, so that means that our loss is equal to 1 over n trace of y minus wx transpose y minus wx, right? And so we expand that out here. You get y transpose y minus 2y transpose wx plus x transpose w transpose wx. That's just expanding out the square here. To find the optimum, just like in the univariate case, we can differentiate and set to 0, right? So just going through, right, we have the dl is equal to, actually let's scroll up so that we can see its expression here. This one right here, right? And so the y transpose y doesn't have a w in it, so we'll get 1 over n trace here minus 2 y transpose dwx plus 2 x transpose w transpose dwx, right? And here, right, it's a quadratic, so that's why we get the two terms. Or the multiplier of 2 here. Let's see. So we can use trace rotation. If you recall, trace rotation is the fact that trace of AB equals trace of BA for any two matrices where multiplying them in both directions makes sense. And so we can take the x and move it over to this side of the trace, and then factor out the dw, and we get this. And so if that's equal to 0, then that means that this guy has to be equal to that guy. And I've just written their transposes down here. Wxx transpose equals yx transpose. All right. So you guys should all be able to do that sort of derivation in your sleep at this point from all of the practice that we had with matrix differentials in the last mini. But in the end, what we get is this system of linear equations, which is a really nice and a really important system of linear equations called the normal equations. And so what this means is that we can find W by constructing this set of equations and then solving. Now, as always, we don't want to solve by directly inverting XX transpose. Instead, we use any standard technique that we want to for solving the linear systems, such as making the LU factorization of XX transpose, and because that's symmetric, the LU is also symmetric, LL transpose. And as a reminder, in this case, the LU factorization is called the Koleski factorization. Then given this lower triangular factorization, we can back solve for every row of W one at a time by making that row of W times XX transpose equal to the corresponding row of YX transpose. And in a lot of systems, in a lot of software packages, there's a very, very simple command to do this. For example, in MATLAB, we just say W is equal to Y times X transpose backslash X times X transpose, right? And so this is the one-line set of code in MATLAB for solving the normal equations, which is kind of cool. If you were a numerical analyst in the 1960s, you would maybe spend your days writing Fortran code to try to make this sort of thing faster. But at this point, all of the Fortran code's already written, and you can call it effectively from MATLAB without ever having to write Fortran yourself, which is a good thing. All right, so that is the math of multivariate linear regression. The math is actually almost the same as the math for univariate linear regression. It's basically, if you remember, what we took was the covariance between y and x and divided by the variance of x. And here, this is essentially that same thing, covariance divided by variance. It's just the matrix generalization. So that's the, like I said, that's the math, but we don't just want the math, we want to understand how to use this tool. And so that's going to be basically what the rest of this set of lecture notes is about. So the first thing for actually using this tool is nonlinear transforms. Like many other places in machine learning, we are very, very happy with features. We love features. And in particular, if we want to model the case when the expected value of y is a nonlinear function of x, so for example, here's a case where the expected value of y is just a quadratic function of x. If we want to do that, then we can do a feature transform. Phi of x is x and x squared. And then given this, we can learn a quadratic function that's a linear combination of x and x squared. Remember that the constant feature vanishes because we've centered our data. Now, of course, it can get a lot more complicated than this. If we have multiple inputs, every feature can depend on any subset of them. So for example, this here, where we have x1, x2, x1 squared, x2 squared, and the product of x1 and x2, that lets us learn a quadratic function on 2 inputs, right? Once we've done the feature transform, we just replace x by phi of x, right? So we learn a matrix W so that y is approximately W times phi of x. And it's still called linear regression, even though phi might be nonlinear. And the reason for that is that it's linear in the parameters, right? So here, W appears just as a matrix multiplication. And it's also linear in phi of x. And of course, the other reason is that we don't have to worry about it for algorithms. We just replace our feature matrix X by the recalculated, the expanded version of the feature matrix where we calculate phi of X. And then we proceed as if everything were normal, as if everything were just before. And so to keep notation simple, I'm not even going to write phi of X. I'll just write X. And we'll just assume that if we wanted a feature transform, we went ahead and applied it. Now, a little bit of a practical consideration. You might wonder whether to standardize first and then apply the feature transform, or apply the feature transform first and then standardize. And if you think about that for a little bit, you can figure out that if you standardize second, then your variables are actually guaranteed to wind up having 0 mean and unit variance, and so that's the way you should do it. Whereas if you standardize first, your feature transform might mess up the centering and scaling of your random variables. So just like always with features, the features can depend on any subset of our input variables. We'll say that a feature depends sparsely on these variables or is sparsely connected if it depends only on a small subset. So if we have 27 variables x1 through x27, then the feature x3 times x7 is sparsely connected, whereas the feature that's the product of all of them is not. And these sparsely connected features are pretty important in linear regression because just in practice we often find ourselves in the case where, okay, it's not actually, y is not actually a linear function of x, but if we add a few of these interaction terms, a few nonlinear functions of small subsets of our original inputs, then we can get a pretty good approximation to a linear relationship. So one example of that is if our input features are binary, right? So x1 and x2 can both be 0 and 1. If we have just those two features, then we can't fit any function of any two-argument function of x1 and x2. But if we add the interaction term, x1 times x2, that is 1 when both x1 is 1 and x2 is 1. That lets us, then we have basically 3 total degrees of freedom. The coefficient of x1, the coefficient of x2, and the coefficient of x1 times x2. And that means that we can fit any function of these variables because there are 4 settings of x1 and x2, so to determine f, we just have to say what its value is for each one of those 4 settings. That's 4 degrees of freedom. But then we lose 1 degree of freedom by centering, by constraining the expected value of y to be 0. And so the 3 weights on the 3 features, the 2 original ones in the interaction, that lets us match those 3 degrees of freedom and therefore match any function of these 2 random variables. And more generally, if we have k binary variables, there are 2 to the k minus 1 degrees of freedom in choosing a function of those variables. And there are 2 to the k minus 1 non-empty subsets of those k variables. And so, unsurprisingly, if we add all of these interaction terms, ranging from x1 times x2 to x1 times x2 times x3 to the product of all of them, if we add all those interaction terms, we can match any function. And of course, we don't probably want to do that because having 2 to the k minus 1 parameters is a lot of parameters if k is at all large. And so we would potentially need a very large amount of data to be able to fit all of those parameters. And so, like I said before, we will search for sparsely connected ones that are relevant. We'll search for small subsets of our variables that seem to have an influence on the value of y. So interaction terms are that's basically where they come from, is when all of the inputs are binary, because people would try and make a prediction based on binary variables. Say, did we treat the patient or not, or did we give them drug A, B, or C? And look for changes in the output, let's say changes in the disease progression, based on changes in the input. And if 2 binary features interacted, then you could completely model that interaction by adding x1 times x2, by adding their product. The situation's a little bit more complicated for continuous input variables. There's, a very large number of functions that you can have of 2 continuous input variables, infinitely many. But the same general idea applies. You look for small subsets of your input variables that make a difference to the output y, and you try and construct some simple nonlinear function of those small subsets. So for example, you could construct a spline, or you could construct a low-order polynomial. So here's like an example. If we had, x is equal to a vector with, I don't know, 1, 2, 3, 5, 4, 7, 2, right? So a vector with that many components, which is 7 of them. We could take a mask, let's say, a sparse vector that's, let's say, 0 in most places and non-zero in only a couple of places, right? And then we could apply a so this is confusingly written. So this here is x. This here is what I'm calling psi. And then we could add a function which was, let's say, the cosine of that thing, or that thing squared, or the 7th Chebyshev polynomial of that thing, right? So we could add, right, we select a sparsely connected feature by picking a small subset of the coefficients of psi to vary, and then applying a fixed nonlinearity. All right. So one of the most common and perhaps useful examples of feature transforms. So interaction terms are one example of a feature transform. Dummy coding, which we're about to talk about, is another example. So dummy coding lets us handle categorical input variables or output variables, meaning things like a day of the week, or a gender, or a state out of the United States. So a lot of times when somebody gives us a data set to start out with, categorical inputs will be represented as small integers. 1 for the alphabetically first state, which happens to be Alabama, 2 for Alaska, 3 for Arizona, all the way up to whatever the last one is, maybe Wyoming. Anyway, whatever the last one is. So if you leave the categorical input as an integer, you're going to get some sort of weird behavior, right? Because linear regression is always going to predict that the output is a linear function of the input. And so, if you move from Alabama to Alaska, you get a change of W, because 2 minus 1 is 1, right? And so you get just 1 times W. If you move from Alabama to Arizona, you get a change of 2 times W, right? And if you move from Alabama to Wyoming, you get 49 times W. And that's kind of weird, right? There's no reason that the difference between Alabama and Wyoming should be 49 times as big as the difference between Alabama and Alaska. And so we don't want to do that. And it's a very common mistake to not notice that your data comes to you this way and not fix the problem. So what we do instead is we make a dummy code, which is we expand our single categorical input into a whole bunch of binary inputs. And each one of the binary inputs is just the indicator for whether your categorical feature takes a certain value or not. So you could have a feature that's 1 when you're in Alabama and 0 otherwise, another one that's 1 for Alaska and 0 otherwise, and so forth. And the reason this helps is that after we do dummy coding, instead of 1 weight for all 50 states, we have 50 weights, 1 for each state. Right? So that means that we can separately learn the effect of moving out to Alabama versus the effect of moving to Alaska versus the effect of moving to Wyoming. Now, a small caveat is that when we construct a dummy code, if there are 50 US states, we'll typically only have 49 separate variables. We'll pick one of the values as a default and omit its dummy variable. And we'll see later that this is going to help with a problem called rank deficiency. Now, this is actually, so first of all, you don't necessarily have to do this. You can leave all of them in and apply some variable selection method to pick the subset of the states that, that matters. So that's one possibility. Or you can apply some sort of regularization, and that avoids the problem of figuring out which one to drop. There's a question, would dummy codes take a lot of memory? Yeah, potentially they could. Now you can always represent them as a sparse matrix, in which case they take no more memory or only a small constant factor more memory than the original variable. But then you get into all of the problems that you can have with sparse matrices. But yeah, if you have you know, something like zip code, which can have a very large number of possible values, you would not want to just naively dummy code zip code. But it would be very important not to leave zip code as an integer, because you know, moving from CMU at 15213, right, to where I grew up, which is zip code 01002, that would have a huge effect. Whereas, you know, you could, yeah, there's no reason that the numerical value of the zip code should have anything to do with the output. So you pretty much have to dummy code zip code, but you you can't do that without doing it as a sparse matrix. Now, one thing that you can do is you can cluster different values. If you have a very large number of categorical values for a particular variable, like zip code, you can try and cluster them using either some external information like geography. You know, you'd cluster together maybe the greater Pittsburgh metro area. Or you can try and do it using statistical information, like the values of some other variables are highly correlated for, you know, 15213 versus 15228, both of which are in the greater Pittsburgh metro area. Yeah, so dummy variables could cause a lot of problems with memory, but often you're just fine, either because there aren't that many different outputs, not that many different values of the variable, or because you can do it with sparse matrices, or because you can cluster related ones together. Okay, so what was I saying? Oh yeah, so dummy codes, you don't have to omit the default value because, you know, you might be doing, let's say, variable selection or regularization later, but it can actually help you with interpretation, because sometimes your categorical variable will have one sort of desired or typical value of the feature. Let's say a patient who's healthy, or a machine that's working, or something like that. And then if you omit that one, then that means that if you set all of the that means that that most common one is represented by all of the dummy variables being 0. And so you think of that as like the default state of affairs, and then each one of the weights of one of the other dummy variables represents what happens when you move away from that default state. So for example, if a patient, instead of being healthy, has disease A or has disease B, what's the change in let's say the number of days that they have to take off of work or something like that. If you don't have a typical, there's not always a typical value of the variable, right? Like if you have a US state, right, there's no one US state that's better than all of the others. At least no one that everybody agrees is better than all of the others. But what you'll typically do in that case is just pick the most common value as your default value. So you'll default to having people live in California, which is the most populous state. Or if you have a binary variable, well, I guess you don't need to dummy code a binary random variable. But if you have like your favorite food, which is a, you know, a categorical variable with a few things, maybe chocolate is the most common favorite food, even though it's no better to have chocolate as your favorite food than it is to have ice cream as your favorite food. And so you'll just pick that most common one as your default. I'm not saying anything about the value of chocolate ice cream here. All right, so these sort of feature transforms are basically how we set up our multivariate regression. And if we do a good job, excuse me, if we do a good job setting up our linear regression, then we'll get good results out of it. Now, commonly, of course, something goes wrong. We set up our regression and something unexpected happens. And so it's really important to be able to detect these problems, figure out what the problems are, and hopefully fix them. Or at least include them in a footnote somewhere so that other people know about them. So last time around, we talked about all the problems that univariate regression can have. In particular, we talked about outliers, heteroscedasticity, which means that the variance is not constant. The variance of y depends on what the values of x are, and nonlinearity. And so all of these problems are also present in multivariate regression. And there's a new one, a new common one called collinearity, or sometimes multicollinearity, or rank deficiency. And we're going to talk about that one later. And the tools that we had for detecting these problems are basically the same in the multivariate case as they are in the univariate case. For example, making a residual plot is almost always a good idea. A residual plot, to remind you, is you plot the predicted value, y hat, versus the residual, y minus y hat. And if you know, a good residual plot will look like that, right? Sort of, you know, more or less a horizontal line and a kind of a narrow cloud. A bad residual plot will have some problems. For example, you could have an outlier here, right? A point way up here that is clearly not on the same wavelength as all of these other points. Or you could have heteroscedasticity, right? Which means that the variance of y is very different at one end of the plot than the other. Or you could have you know, nonlinearity, right? Where you know, on average this thing is constant, right? It's, you know, still averages out to 0, but you can see there's a clear trend that there, you know, points here are bowed up and points here are bowed down from the line. So, and the fixes are actually more or less the same as they are in univariate regression, although actually they, we have more tools available in a multivariate regression because we can add more features. So, in particular, we can fix potentially heteroscedasticity or nonlinearity by looking for new feature transforms or new interaction features that make the expected value of y closer to linear and the variance of y closer to constant. And that is actually, like I was saying, easier in multivariate regression because the regression can actually help us on its own. So, for example, if we think that, you know, instead of being a linear fit from our inputs, y is a low-order polynomial fit, and we don't know which low-order polynomial, well, instead of trying to guess what low-order polynomial and undo that transformation, we just put in a whole bunch of monomials as features and let the regression figure it out. And then I mentioned outliers as well. The usual fixes for outliers are to try and detect and remove them, or to use a robust loss function, or both. And those still work here in multivariate regression. There's also another tool, which I'll show you an example of in a sec, called a scatter plot matrix. As a matter of fact, why don't I just go ahead and bring up a scatter plot matrix. Let's see. So here is what a scatter plot matrix looks like. So what do I have here? This is a data set which has 1, 2, 3, 4 inputs and 1 output. Actually, all I can tell from this is that the total of inputs and outputs is 5, but I'm telling you that the first 4 are inputs and the last one's the output. And what each one of these subplots is showing, for example, this subplot here shows a scatter plot of x1, the column, versus x2, the row, right? And so this one here, you just flip it across the y equals x line. One of the you're just plotting x2 versus x1 instead of x1 versus x2. And here we have x1 and x3, x2 and x3, and so forth. And so this scatter plot can show us a bunch of things. It can show us, relationships between the variables. It can show us here there are clearly some pretty bad outliers in y here. It can show us weird things about the histogram, right? So you can see here there are only 4 distinct values of x4, right? Because there's 4 horizontal lines. And so that means that this was probably a categorical variable that we should transform into a dummy code. So you can see all sorts of things from a scatter plot. I guess you can also see, like here, there's a slightly curved relationship, right, that we can see there. So we can detect sort of nonlinear relationships as well. Oh, I should also point out that the diagonal elements here are excuse me, histograms of each one of the variables. It's traditional to do that rather than scatter plotting, x4 versus x4, because it's easier to read a histogram than it is to read a scatter plot of a variable versus itself. All right, so that's tools for detection and diagnosis of all of the problems that come forward from univariate regression. So the new problem, the problem that's specific to multivariate regression, is rank deficiency. So what is rank deficiency? Rank deficiency, the unhelpful way of saying it is that in the normal equations, the matrix XX transpose that we have to solve, we have to invert in the linear equations, except that we shouldn't actually invert it. If that matrix is not full rank, meaning that it's not invertible, then that's rank deficiency. I'll get to its actual, maybe more geometric meaning in a sec, but I want to point out that if you ask a software system like MATLAB or SciPy to try and solve your linear regression, your normal equations for you, many of them will actually just detect when this is happening and warn you. So MATLAB will say something like, matrix is close to singular or badly scaled, right? I've seen that warning message way too often in my lifetime. All right, so you can detect it pretty easily because you'll just get a warning about it. Geometrically, what it means is that one of our input features is a linear combination of some of the other input features. So what does that mean? Get ourselves a fresh page here. So let's draw a problem with let's see, 4 training examples, right? So we have x1, x2, x3, and x4. And let's just say that they just happen to be equally spaced. So we'll call them 1, 2, 3, and 4. Right? And then we have 4 y values, y1, y2, y3, and y4. Right? Now, we're going to center the y values. And so we have a constraint. Let's say y4 is equal to minus the sum. Well, rather than writing it as the sum, minus y1 plus y2 plus y3, right? And so if I want to plot my training data, I can plot y1, y2, and y3, right, as a point in 3-dimensional space. Let's say this one right here, right? And then similarly, I can plot each one of my input features as a different point in 3-dimensional space by dropping the fourth possible value of it, right? So I can center it and draw it as a vector in 3-dimensional space, right? So maybe, so this here, we'll call this y, right? And we'll say that we have, let's say, the first feature is turned on only for the first example, let's say. And then let's say maybe the second feature is turned on for the first 2 examples, right? So what I'm trying to do in my linear regression is write y is equal to wx, right, which is equal to, here it's just, there's one real valued output, so, and let's say 2 input variables, so that's w1 x1 plus w2 x2, right? So I can think of each one of my input features as being a point in n-1 dimensional space, right? And what I'm trying to do, so rather than get exact equality, I only need approximate equality. What I'm trying to do is find some linear combination of x1 and x2 such that y is maybe let's say this point here, right? So let's call that w1 x1 plus w2 x2, and I would like this distance, right? Y minus wx to be small. Now, I should warn that because I dropped the 4th coordinate here, the distances are not actually perfect. I've altered the distance to be slightly different from Euclidean, but the intuition still holds. We want a small distance between y and the linear combination of the x's. Now, if I happen to have a third x, which is, let's say, this one, x3, right? X3 could be in the span of x1 and x2, right? That means that for any given, there's some set of weights, let's say 4 and 7, such that 4x1 plus 7x2 is equal to x3 for every training example, right? And that's what I mean by rank deficiency, right? That will result in the matrix X being rank deficient, right? So the typical shape of X is like this. We'll have P features and N examples. Right? And so rank deficient would mean that the rank of X was less than P. Right? You could also have it the other way around, more features than examples, and then you would actually always have rank deficiency in this case. You would never get XX transpose to be invertible. So so rank deficient, let me actually write that. In this case, rank deficient is the same as saying rank of X is less than P, right? When we have P features and examples. And so, like I said, geometrically rank deficiency means that one of our input features is a linear combination of some of these other input features, where we're thinking of now the rows of X, meaning one feature across all n examples, as being a vector. How does rank deficiency happen? Well, it's easy to do it accidentally. You can add a duplicate feature by mistake. Let's say you just accidentally add 2 copies of X1. That's pretty easy to discover and avoid. Maybe more interestingly, you can spread out the rank deficiency across a few features. For example, let's go back to dummy codes. If we make a dummy code with a feature for all 50 states, right? Then what happens if you add together all of those dummy features, right? So you add together the indicator of being in Alabama with the indicator of Alaska and so forth up through all 50 of them. Well, let's assume that we're talking about points that are gathered in the US, then every single point is going to have exactly 1, 1 in one of those features. And so when you sum them together, you're always going to get the constant 1. And then when you center, right, that means that the sum has mean 1, therefore the sum of the centered ones is going to be, you subtract off 1, right, and so you'll get mean 0 from the sum of all of these centered dummy features. And so that means that the dummy features themselves are linearly dependent, right? Because the definition of linearly dependent is that there's some linear combination that gets you the 0 vector. And here the linear combination is just to add them all together. So that's a fairly common way of having subtle linear dependence. And as you start to make more and more complicated feature transforms of your data, it's easier and easier to accidentally introduce a linear dependence. Maybe an even more subtle version of rank deficiency is when you happen not to have enough data to distinguish different features. So, for example, suppose you have a binary feature that's really commonly 1 and only rarely 0. So let's say, likes chocolate is a binary feature, and most people like chocolate. And so if you sample only a few people, you might think that all people like chocolate, right? You ask 5 of your friends all say they like chocolate, and so you generalize to thinking everybody likes chocolate. And what that would, obviously that's a false generalization, but what that means is if those 5 friends who all like chocolate are your data points, then you're going to think that the chocolate feature is constant, right? Because it's constant in your training data set, and so it's going to wind up leading to linear dependence. Maybe even more subtle is if you have 2 features that are highly correlated, right? So liking 2 different types of nuts, walnuts and pecans. If those features are highly correlated, you might see some people who like both and some people who like neither. But if you don't have a lot of data, you might not see anybody who likes walnuts and not pecans, or pecans and not walnuts. And so you might think that those 2 features are linearly dependent, because they would be linearly dependent in your data, even though they aren't in the real world. All right, so rank deficiency is really easy to have happen, and it comes all over the place. So how do we fix it? Well, first, I guess, what problems does it cause? So the first one is computational. We get, MATLAB gives us a warning message and gives us an inaccurate answer because it's trying to invert a non-invertible matrix. And that turns out to be really easy to fix, right? You can just fix some of your weights to be 0, so some columns of W to be 0, and you keep doing that, which amounts to dropping rows of X until all of the remaining rows of X are full rank, right? And you can do it in random order. It doesn't matter what order you do it in. At least the number you drop will not depend on what order you do it in, although you might get a better or poorer conditioned, numerically conditioned problem by doing it in one order versus another. All right, so you can fix it really easily just by dropping features. And in fact, that's what we're recommending for the case where you included all the dummy variables, right? You drop specifically the feature that corresponds to the default or the most common value of your categorical variable. A slightly more complicated, but maybe numerically safer strategy is to use singular value decomposition. So if X is low rank, then when you SVD it, you SV transpose, some diagonal elements of S are going to be 0. And so you just drop those and drop the corresponding columns of U and V and replace X with, let's say, V transpose. Right? And so that can cause fill-in if X is a sparse matrix, but it can make the resulting normal equations really well conditioned. So that's only, it's only a temporary hiccup rather than a real problem. The real problem is with interpretation. So I want to stress, you don't always have to interpret the weights of a linear regression, right? You can just use a linear regression for prediction. But if you want to try and figure out what do the weights of your linear regression mean, then when your input features are linearly dependent, you have a choice, right? You could use feature 1 or feature 2, where feature 2 is perfectly correlated with feature 1. And if you're trying to explain something, then you don't know whether feature 1 or feature 2 is the real explanation. And in some sense, there's no way to tell unless you can go out and get yourself more data where you have a sample that differs on its values of x1 and x2, right? And like I said, it's only a problem with interpretation because our predictions are the same, right? It doesn't matter for our predictions, they're going to be the same no matter which linear combination of the two features we use. But that's maybe not so comforting if you were hoping to figure out which of the two variables is the one that's actually associated with y. And so because it's a problem with interpretation, which is sort of a difficult thing to do anyway, it's going to be sometimes hard to fix, right? Diagnosing it can mean sort of staring at our data and trying really hard to understand the features, understand the underlying meaning, what happened to give us the features. If we're lucky, we can quickly discover a bug, such as accidentally including all of the dummy variables, or accidentally including two copies of x1, or accidentally including a constant feature and then centering it so that we get the 0 feature. Right? I've done all of those things, and hopefully they're relatively fast to fix. But in general, we're just stuck trying to figure out more about what's going on. I want to point out as well that interpretation can be a problem even if our features are only approximately linearly dependent instead of exactly linearly dependent. Because if our features are really highly correlated, that means that, well, let me say it this way. Suppose there's a direction for W, call it W0, such that that linear combination of features is 0, or is very near 0. So W0 times X is near 0. In that case, it's going to be really hard to, right, if it's exactly 0, it's impossible to figure out what the coefficient of W0 is in the final W. Or maybe a better way to say it, what is the projection of the final W onto W0? And if W0 times X is only very small, then it's going to be really hard to figure out what the projection of W should be onto W0. And what I mean by hard is that if we have any noise whatsoever, we'll need really large amounts of data to be able to figure out what that proper value is. So it's important, and again, this is only a problem for interpretation, right? Our weights are unstable, but the actual predictions are not. But you know, we may still need to fix it, and so we can diagnose approximate rank deficiency with an SVD, the same as we can do exact rank deficiency. Instead of having exact zeros on the diagonal of S, you'll have some just really small entries. You'll have some that are, you know, let's say 10 to the 5 times smaller than others. And so we can fix it the same way, right? Like if we only care numerically, we can just drop the small singular values. But if we care about interpretation, we have to either find the bug in our feature construction or go back and understand why this linear combination is so near to 0, why these features are so strongly correlated. So somebody is asking me about the advantages or disadvantages of using an orthonormal basis, right? So let's just make that a little more precise. So if we have X is equal to U S V transpose, right, where let's assume X is this shape, fewer features than examples, that means that U will be P by P, S will then also be P by P, and V will be P by N, right? So, or V transpose will be P by N. So V is N by P. So orthogonalizing would mean using, let's say, just V transpose, right? So we could replace X by V transpose, right? And we can combine orthogonalizing with dropping small values of S, and so that would mean by, or by a subset of the rows of V transpose. Yeah. Right? And so that is, again, it's not going to change our predictions at all, right? So we're free to do that if we feel like it, if we only care about the predictions. What's going to happen is that for orthogonal rows of X, that's going to maximize the stability of the matrix W in terms of small changes in our data. And so we will have constructed features that for which we can very stably estimate the weights. So that's a good thing. But we may have done some bad things as well. First bad thing is that we may have caused fill-in, right? So if X was sparse, then there's no reason that U or V would be sparse, and so we may have given ourselves some dense features instead of sparse ones, which can cause computation problems. And the other is interpretation, right? If the original rows of X were things like, height, weight, gender, and favorite, whether they like chocolate, right? Those are all sort of moderately interpretable, and that means that their weights are, what's the effect on Y of liking chocolate, right? Whereas X is just some, arbitrary looking linear combination of the original rows of X, right? So V transpose is a linear combination of the rows of X. In particular, we get that S inverse U transpose X is equal to V transpose, right? That follows from the SVD. And so this here is a linear combination of the rows of X. And that linear combination might make things a whole lot harder to interpret. So orthogonalization helps with numerical stability of the answer, and it hurts sparsity and interpretation. So it's your choice which of those things you find more important, therefore your choice of whether to orthogonalize or not. All right. So I wanted to point out this didn't really fit in anywhere, so I put it at the end, but there's one common mistake that people make a lot of times. And that mistake is in how to apply standardization. So in particular, when you're standardizing, so stepping up a level, when we make a predictor of any kind, when we learn it, it's important that that predictor should depend only on the training data. If we let it depend on something else, let's say the test data, then we can get an unnaturally good estimate of its performance, right? It will if we leak some dependence on the test data, we can have a unnaturally low residual error. And so when we're standardizing, that holds as well. And so that means that the parameters of the standardization are the means and variances of each feature, right? We want to subtract the mean and divide by the standard deviation. And so we have to calculate those parameters from the training data only, right? And so if we're if we're cross-validating, we have to recalculate them from every fold of our cross-validation, right? So every time we run our learner, it has to, as its first step, do the standardization, if we're going to standardize, right? So for linear regression, it's a good idea to standardize. For other machine learning methods, it might or might not be a good idea to standardize. All right, so what that procedure looks like is we'll compute the training set means and training set standard deviations, and then standardize our training data, subtract the mean and divide by the standard deviation in the inputs and in the outputs. And then we record these guys, training sets, means, and standard deviations, for later. Then at test time, somebody's going to ask us about a new vector x, a new input vector, and we standardize it using the training mean and standard deviation. Then we've learned our w, so we multiply our standardized x by w to get a prediction of the standardized y, and then finally we undo the standardization for y to get a prediction of the original version of y, meaning that we multiply by the standard deviation and then add back in the mean. And this is again using the training set, means and standard deviations. And so I've seen a common mistake is to have your set of test data and standardize it using the same function that you use to standardize the training data, which is to say that you subtract the test set mean and divide by this test set standard deviation. And that's bad because it means your predictions depend on the test set mean and test set standard deviation. So don't do that. All right. So I wanted to do now an example. And I think we have time to get started on it before class ends. So I will go and do that. And the example is actually this data set that I showed you the scatter plot matrix for. So let's suppose that we wanted to learn a linear regression predictor for this data set. Right? We want to predict y from all of the x's. So I want you guys to look at this and think about what you think the first steps should be in constructing that linear regression. And to me, there's at least a couple of steps that are obvious. And so after you guys have a couple of minutes, maybe you want to write them down on a piece of paper so you can compare. After a couple of minutes, I will say what I see in this data, and we can compare. All right, so I guess what I see first is that there's this categorical variable, right? The fourth x has only 4 possible values. Looks like 1 is the most common and 4 is the least common, right? Because there are fewer points up here than there are down here. And you can see that from anything in, I mean, you can see it from the histogram, and you can see it from any one of the plots in this row and column of the scatter plot matrix. So the first thing that I'm going to do is dummy code this variable, right? And the way I'm going to do that is I'm going to take my original feature matrix, keep the first 3 rows of it, and then add rows for whether the fourth one is equal to 1, whether it's equal to 2, whether it's equal to 3, whether it's equal to 4. And in fact, because it's a dummy code, I will skip one of the values, and I'll skip the most common one, which is x equals 1. Right? And the other thing that I notice about this is that if you look at the scales here, they're kind of small numbers, but you can see very easily that these scales are much larger than they would be for standardized variables, and so I'll standardize them. And so let's start getting some code for you guys to look at. So here's a, maybe we'll put this over here so it doesn't obscure the plot. And so the first bit of code that I would run is this. Let me put this here. All right. So you can see that, right? This is the first 3 rows of x, followed by whether the fourth is 2, whether it's 3, and whether it's 4, right? And then the other thing that the next thing that I would do is I would standardize. Here is the code for standardizing, right? So I'm taking the mean of features. So mean in MATLAB, it takes a dimension to take the mean along. So this is along every row. And then the same thing for standard deviations, mu's and sigmas, standard deviation of each of the features. And then I use broadcasting, that's BSX fun in MATLAB, to divide each, to subtract mu, the mean, from every corresponding element of features, and divide the result by sigma. And then finally, because y is just a single one, I can just do it the easy way, y minus mean of y over the standard deviation of y. So if I go and run that, it looks like this. Right? So now if we go here, right, so I have my 3 original features, and then I have 3 binary features, y equal 2, 3, and 4, or sorry, x4 equal 2, 3, and 4. And now I've got my scatter plot matrix, and it's standardized, and you can see this second obvious problem that I was noticing, which is there's at least one really bad outlier in y, and maybe these are sort of too close together to tell. Maybe you can see it a little bit better here, right? There are maybe a couple more outliers there. So the next thing that I would do to this is try to remove the outliers. And the way to remove the outliers is, I guess there's a couple of different things we can do, but the sort of my first approach to removing outliers would be to make a linear fit and look at a residual plot and identify the points with very large residuals as possible outliers. Right? So here is the code for a residual plot, right? So this is my linear regression, right? Y transpose x, yx transpose divided by xx transpose. My residuals are the y minus the prediction, and so a residual plot is to plot the prediction versus the residuals. And if I do that, here is what happens, right? So this is kind of interesting, right? So you can see, here's most of our data, but there's one point way down here which makes the plot scale such that all of our original data is some tiny little blob up in the corner, right? And then there's another one up here that's maybe not quite as bad. And so I can go and manually try and remove these guys. And so let me show you what that looks like. So looking here, right, it looks like the residuals are maybe the ones for which the absolute value is greater than or equal to 1.5. The absolute value of the residual, like all of these points are between plus and minus 1.5. So let's go ahead and remove all of the points that have residual greater than 1.5 and redo the fit. And so that looks like this, right? And now we're looking at it again, and now that we've blown it up a bit, we can see that in fact there are probably more outliers than that, right? So this guy up here is probably an outlier, and I would say that probably all of these guys are outliers too, right? And then, like you can see here, right, like most of the data is, there's a curve down here, and there's a few smaller, but still probably outlier points that are below that curve. So let's first try and get rid of these guys. So I'm going to update and remove everything whose residual is bigger than 0.4. Let me go ahead and do that. And that's what it looks like. And so you can see that the fit is getting nicer and nicer. And now you can see that there are these guys down here, right, which seem to be fairly low for their value. And so what I'm going to do as well is remove them. So it looks like maybe all of their residuals are less than minus 0.1. So let's remove that. And there we go. Okay, and so now we've done a pretty decent job of removing outliers. right? And we can go back and do our plot matrix again, and it should be a lot easier to look at now that the outliers are gone, right? So you can see that like these plots that were really tiny before because they were scaled to contain all of the outliers, they're actually filling up more of the corresponding box. So this is sort of a much nicer thing to look at, right? And so I think I'm going to stop there with our example, and we'll continue it. We'll continue it at our next class. So office hours starts now, and feel free to keep asking me questions in office hours. Talk to you guys later.